Welcome back, students. This lesson is about LeChatelier's principle, specifically focusing on manipulating concentration. Okay, so LeChatelier's principle states that a system at equilibrium subjected to a stress will shift in a direction to relieve the stress. Okay, so if it's stressed out, try to relieve the stress. Okay, so let's take a look at some of the variables that affect an equilibrium system. So first one, what if we increase or decrease concentration? So here's the rule. When we add a substance or we increase concentration, that causes equilibrium to shift away from the substance added. Here's an example. Let's say I have an equilibrium system and you see it there called Lab 48. All of those substances are in the beaker. And right now we're going to say that it's shifted towards the pink side. So imagine some blue paint and some pink paint mixed together, but there's more pink paint than blue, so the pink is overpowering the blue. So that's the color we see. Even though there's blue in there, we see the pink. Okay, so I'm going to increase the concentration of chloride ions by adding hydrochloric acid. So let's say I stress the system out by adding chloride, hydrochloric acid. The H positive will be a spectator in this case, and the Cl negative is what's getting stressed in the system. By stressed, I just mean we just pour a whole bunch more Cl negative into the system. That causes equilibrium to shift away from the substance we just added. And now the rule is, in my head, I just think of it this way. Whichever way that arrow points, on that side we have up arrows, so those go up. Okay, so those go up, up, and on the opposite side of the arrow everything goes down, because as you saw from the demo there, we consume those to shift it back. We consume the products to shift it back to reactants. So down, down, down. And then, because there's more blue ions now than pink ions, the beaker changes color to a blue. Okay, here's another way to do it. Take the same system. This time we add water. So the stress is water. We shift away from the water. So whichever way that arrow points, everything on that side is up, and on the opposite side it's down. Here is the demo in real life. Okay, so you can see the system here. So the test tube on the left contains all of those things. That's our control. And here I'm adding hydrochloric acid. So it should shift away, causing blue ion to go up and pink ion to go down. There, you see it turned blue. Okay. All right, same thing when I add water. So here I'm adding water. It shifts away, pink ion goes up, as does everything else on that side, and the other blue ion goes down. Okay, so it's shifted back to pink. And there we go. Here's another way to look at it. Here's another one. So let's say we stress this system out by adding into, we shift away, ammonia up, other side down, down. Or what if we increased ammonia? We shift away, whichever way that arrow points, we have up, up, down. Okay, here it is another way. I can decrease the concentration of H2. And the rule when we decrease, up top it says, when we decrease concentration, we shift towards the substance removed. So I think of it this way. If I lost a bunch of money, I would have to do something to replace that money, or as much of that money as possible. Okay, so if I lose money, I shift to replace it, whichever way that arrow points. That side's up, everything else is down. Okay, if I decrease ammonia, that's the stress. I have to replace the ammonia, whichever way that arrow points is up, everything else is down. Okay. All right, here's another way to look at that. So let's say I decrease the chloride ion by adding AgNO3. So that seems a little bit weird. I decrease something by adding something. Now what's going on there? Well, let's take a look. So again, all of those entities in lab 47 are in the beaker. So I see the blue ion, there's water, there's chloride, there's the pink ion. Okay, and now here's what's going to happen. I'm going to add AgNO3. So I just added Ag positive, NO3 negative. NO3 is a spectator, so I'm not going to worry about it. Now, if you check a solubility table, whenever Ag positive is exposed to Cl negative, this happens. Ag positive and Cl negative form a precipitate. Okay, so by adding silver nitrate, AgNO3, the Ag positive grabs onto Cl negatives, and the concentration of Cl negatives actually goes down as the silver nitrate precipitates it. Okay, so that causes a decrease in the chloride ion concentration. So let's watch it. There's my stress. I've added AgNO3, which causes us to shift to replace. So it should turn pink, up, 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 down, down. So this thing should turn pink. I would get the pink ion up and the blue ion down, and here's why. There's my stress. Those two combine and the concentration of Cl negative drops. I shift to replace. Those go down. And those move to the forward reaction, causing a pink to form and a Cl negative and some energy. So I give off a little bit of energy here. The beaker gets a little bit warmer. Same thing again. I caused those two to precipitate. I must shift to replace. Those go down. Those react and form products. Pink appears as blue disappears. And there you have it. Okay, so that's what I would see. What macroscopic property would I observe in the beaker? It'll turn pink. Here it is in real life. Okay, so you can see that I have, there we go. I'm pouring in silver nitrate right now, which is going to cause Cl negative to precipitate and drop in concentration. I shift to replace, down, down, up, up, up. Pink ion goes up. So I'm shaking it up there, and you will see right here, look, there is the precipitate right there. That's AgCl solid. Okay. All right, and notice it turned pink. Okay. Good. All right, watch for the next video on manipulating temperature.